Let's take a closer look at the configuration process. For this demonstration, we will use the AWS IoT platform from Amazon and specifically the MQTT test client. To connect to this platform, the gateway and any other device we want to use must be defined as an IoT thing, as well as have the corresponding device certificates, which can also be created during the same process. If you need more information about this, please check the AWS IoT documentation. Moving on to maps, we are already connected to our gateway and have enabled an indoor unit, which is enough to see the signals we will be using. Signals can be divided into status signals, ending with _S, and command signals, ending with _C. The information from the status signals is shared by the gateway by publishing to their corresponding topics, as we can see in the Publish section. Commands are also managed through topics, although in this case the gateway is on the receiving side. That is, it is subscribed to said topics, as we can see in the Subscribe section. For the MQTT client on the publishing side, to correctly issue a command through the topics the gateway is subscribed to, the topic content or payload must follow a predetermined structure, shown in the Message Payload section here. Regarding the topic structure, it is important to note that there is a specific topic for each unit, so when using them, we must replace the indoor unit placeholder with the corresponding unit ID. The MQTT configuration begins at the connection section. First, select the cloud platform. Currently available options are AWS IoT Core, Azure IoT Hub, and a generic option for other platforms such as Mosquito. We'll select the AWS IoT Core. Next, we must define a client ID. Since all the MQTT clients must have a unique ID, we recommend using the gateway's MAC address, which can be entered automatically by pressing the Use MAC GW button. For the host field, we must use the endpoint provided by the broker. In our case, we can find it in the connection details section of the MQTT test client. You may notice here that the version used by the MQTT test client is 5, but this causes no conflict with the version used by the gateway, which is 3.1.1, as AWS explicitly supports cross-version communication. The most usual ports are 1883 for regular connections and 8883 for secure connections. Usually, we would use the latter as our connection to AWS IoT is a secure one. However, for security reasons, IT departments may block these ports by default. If so, please ask your IT team to enable inbound and outbound traffic on these ports to ensure the system functions properly. As an alternative, AWS IoT also supports communication through port 443, which is used for HTTPS traffic and therefore unlikely to be blocked. In that case, we must define a TLS extension known as ALPN, short for Application Layer Protocol Negotiation. This will be done in the Security section after enabling SSL-TLS. Keep in mind that ALPN is only required if the domain configuration has either the authentication type or the application protocol set to default. Back in the connection section, the remaining parameters can be left as is. You may notice, though, that the port number has automatically changed to 8883. This is because the port number changes automatically when SSL-TLS is enabled, so you should keep that in mind when using other ports, such as the 443 port mentioned before. Moving on to the security section again, since we have already enabled SSL-TLS, we just need to attach the corresponding certificate files. As mentioned, in AWS these are downloaded when defining an IoT thing. Regarding the certificates, these include the 2 certificate authority files for the server authentication, and the client certificate and private key files for the client side. About the use of certificates, it is important to note that the gateway's internal time must be correct for them to be recognized as valid. A simple way to ensure this is by defining an NTP server in the General Configuration section, which the gateway will use to update its internal time regularly. Having done that, we should be able to connect to the MQTT broker to publish statuses and subscribe to commands. Let's save the project and send it to the gateway. After reconnecting, we'll test the connection at the Diagnostic tab. Once in the Diagnostic tab, both the comms and the debug checkboxes at the MQTT viewer should be enabled to get the maximum amount of information. Our test will involve the ambient temperature status signal and the temperature setpoint command signal. We will publish the first one so our test client receives it, and then the test client will publish a lower temperature set point value in response for the gateway to receive it. Since the ambient temperature is published by the gateway through the temp ambient STS topic, our test client must be subscribed to this same topic to receive the messages when published. To subscribe to this topic in the MQTT test client, copy the topic structure and paste it in the topic filter field. Remember to replace the unit placeholder with the corresponding unit ID from the unit. Having done that, press the subscribe button. Back to Maps, we then enter an ambient temperature value in the Diagnostic tab to force a publish to the related topic. For example, 25 Celsius degrees. If everything's okay, the payload should appear in the test client subscription. According to the MQTT viewer, the payload has been received, so let's check our test client. And indeed, here we can see the payload with the published information. Success! After receiving this information, the BMS might want to set a lower temperature set point. The roles would then be reversed, with the test client publishing the message and the gateway being subscribed to it. To publish the message from the MQTT test client, we need the topic and the payload. As a reference, both can be found in the message payload box from the subscribe section in Maps. Enter the set temp CMD topic name in the topic name field of the test client, once again modifying the unit placeholder for the actual unit ID. Then, enter the message payload. As we have mentioned before, the payload format is predefined, so to avoid mistakes, we should also copy the payload from Maps and then set the desired value manually. We'll set it to, for example, 21.5 Celsius degrees. After pressing the Publish button, let's go back to the Diagnostic tab in Maps to see if we have received the information. Sure enough, as we can see, the temperature set point command has changed, showing the requested 21.5 Celsius degrees value. This value would then be applied to set a lower temperature set point for the unit specified in the topic.